So good morning, students.
Morning.
Yes,
Good morning, sir.
good morning. In electrochemistry, we were studying corrosion, and we have taken rusting as an example for corrosion. So corrosion is a electrochemical phenomena. When I say electrochemical phenomena, there will be involvement of gain and loss of electrons. That is electrochemical phenomena. So corrosion is a electrochemical phenomena where metal is lost in the form of its compound by the action of constituents of atmosphere. When I say constituents of atmosphere, it may be moisture, dissolved oxygen in it, and the dust particles, carbon dioxide, everything. So different metals undergo corrosion. Rusting of iron is an example here. You take any iron, any form of iron. When I say any form of iron, there is a wrought iron, there is steel, there is cast iron. Cast iron is the most impure form, wrought iron is the most pure form, whereas steel has moderate percentage of carbon, but it is most useful form of iron actually.
Sir,
So yeah,
ಡಿಸ್ಟರ್ಬೆನ್ಸ್ ಆಗ್ತಿದೆ ಸರ್.
ಹೇಳಿ ಪ್ರಜ್ವಲ್.
ಸರ್ ತುಂಬಾ ಡಿಸ್ಟರ್ಬೆನ್ಸ್ ಇದೆ, ಅದೇ ಮುಂಚಿನ ಅದು ವಾಯ್ಸ್
One second.
ಐ ಕಡಿಮೆ ಆಯ್ತು ಸರ್.
ಅದೇನು ಆಟೋ ಆನ್ ಆಗ್ಬಿಡುತ್ತೆ, ಅದು ಆಫ್ ಮಾಡಿದ್ರು ಕೂಡ. ಓಕೆ,
ಓಕೆ ಸರ್,
ಥ್ಯಾಂಕ್ಸ್. So in that way, iron contains little impurities in it. So the impurities commonly present in iron is carbon. Along with that, some traces of other metals also could be there. Okay. So when iron is exposed to the atmospheric condition for long time, so you may ask, why should we expose iron to the atmosphere? Iron is used in construction. Iron is used in automobiles. Iron is used extensively everywhere, right? So iron is one of the most versatile elements, which is most significant for us. So be it construction or automobiles, when it is exposed for a long time in the atmospheric condition, so rusting starts. What actually happens? Iron acts as anode, undergoes oxidation. The impurities such as carbon and other trace elements act as cathode. The moisture which deposits on the surface will behave like electrolyte with dissolved oxygen. Okay. So thus, wherever impurities are there, the iron and the impurities together form tiny voltaic cells. So many voltaic cells will be there in a small sample of iron. And thus, when I say voltaic cell, there is oxidation, there is reduction, quite evident. So anode, iron undergoes oxidation, losing electron. Those electrons will be gained by oxygen in presence of H plus there. It reduces to water, and then Fe2 plus thus obtained will further undergo oxidation to Fe3 plus, and then Fe3 plus combines with oxygen and water to form finally hydrated ferric oxide. The hydrated ferric oxide thus formed is nothing but rust. So that kind of yellowish compound which is formed on the surface will just be adhering there because of the mechanical stress or air pressure. It will peel off and fall into the atmosphere. New metal will be exposed. This process continuously take place. So in a matter of years, the metal will be lost in the form of its compound, which is not a desirable process, and it also can be hazardous because metal is used everywhere in automobiles and all. If we axles and all those things where the metal iron is very crucial, if it is completely undergone rusting, then the vehicle may collapse. Correct. So in that way, we need to prevent the rusting of iron. It is a spontaneous process which sets up in the atmosphere and takes place by itself. But in order to prevent, we have to avoid iron undergoing oxidation. That is the triggering reaction, right? If iron doesn't undergo oxidation, then the entire process of corrosion, that is rusting, would not take place at all. So let us see which are all the methods we can adopt to prevent rusting. Okay. Yes. So we'll see now. Rusting. Methods of prevention of rusting. So when I take up that, number one, there is temporary methods which are being employed. Those temporary methods, they are generally called barrier protection. Barrier protection. That means there is a iron sample which is in contact with the atmosphere. That's why it is undergoing rusting. What you need to do, you take that iron, it may be a rod or anything like that, coat the surface with paint or oil or any other substance. A thin coat of paint, oil or grease, such kind of material will be coated on the surface. Okay. So when you coat with a thin layer above the surface, so what would happen? So there is a kind of protection where iron will not be allowed to interact with the elements of atmosphere. It's a very thin layer. That's all. But this is a temporary method. As long as the coating is there, paint can peel off. It may be matter of 1, 2, maximum 3 years. So there may be little peel that may come out. At the point of peel only, there may be a small, very small opening, but still iron starts undergoing corrosion. Okay. Even oil, grease and all will dry off. There will be no long life for that. But you have to keep repeating. That's why painting will be repeated for every 2 years or 3 years maximum. Okay. Otherwise, the iron article starts rusting. Okay. This is barrier protection for you. Next, something called as galvanization or galvanizing. So what is galvanization? So especially in this galvanization method, iron to be protected from rusting will be connected or coated with zinc. Okay. So iron article is coated with zinc. Now in the electrochemical series, if you can remember, zinc is above and iron is below. So we know that in electrochemical series, upar wala deta hai, niche wala leta hai. Okay. So zinc will give electron, iron will take electron. Now why iron is undergoing rusting? Because it is acting as an anode. Iron is acting as an anode. That's why it is undergoing oxidation and rusting. If zinc is coated, pardon me, mute the mic, please. So if zinc is coated above iron, zinc being more electropositive, or zinc having low SRP than iron, or zinc being above iron in the electrochemical series, zinc can act as anode and iron becomes cathode. Okay, so that means the moment you coat zinc, zinc will become anode and thus iron will be protected from oxidation. So here zinc undergoes oxidation and because it acts as anode due to low SRP, okay, and protects iron from corrosion. Iron from undergoing oxidation and thus from corrosion. Rust. Okay. So this is the thing. Now zinc slowly depletes, will be lost in the form of its compound, and after sufficient time, this method may be much sustainable and can protect iron for very long time. But again, if zinc is once completely gone, you have to coat the iron with zinc again, but that takes years together. Okay,
Sir,
so
can
this
you
is
scroll up, sir?
uh, this is also called
Sir,
sacrificial method of protection of iron.
can
Somebody
you scroll up, sir?
ah, oh, is that okay?
Thank you, sir.
Yeah. So this method is also called sacrificial protection, because for the sake of one, another is sacrificed. Zinc is sacrificed for the sake of iron. So therefore, this is sacrificial protection. Okay. So this is the thing. Now, one note here for you, or I would I have given you in your material as also know that act. Let's call it with new terminology. Act. Also know that. So instead of zinc, there are methods like tinning. Not thinning, tinning. Okay. So what is tinning? That means coating zinc with the coating iron with tin. Okay. There is a difference between this galvanization and tinning. Zinc is above iron, whereas tin is below iron actually. So tin has high SR. So since tin has ISRP, when it is coated onto the surface, what would you think? Then, sir, it is like iron undergoing oxidation. No, no, that is not the reason why tin is coated here. Tin is very stable towards oxidation. And it has a kind of stability like noble gases. Okay, it would be least reactive. Since it is least reactive, the tin is coated onto the iron surface, and as long as tin coating is there, there is no problem. Thin layer, very thin layer they give. It is not like one rod will take and connect one more rod. Very thin layer of tin will be given. That's all. As long as that layer is there, iron will be protected. The moment that layer, due to friction or something like that, it breaks, then what would happen? Then the moment the tin breaks, the iron starts undergoing corrosion at a faster pace than it would undergo corrosion in the atmospheric condition without iron, without tin. Why it is so? Can anybody explain? Why would, if tin breaks on the surface, why would iron undergo faster rate of corrosion than if it were to be alone in the atmosphere? What could be the reason?
Tin is electronegative.
See, it is because there is more support for iron to become or behave like anode and undergo oxidation rapidly. Because tin has high SRP, when you connect high SRP metal to iron, then obviously oxidation will be happening at anode, that is iron, more rapidly than if it were to be alone. Okay, but as long as tin is there on the surface as a coat, it can be very much protected. That is one thing which is really a point to be noted. Tin should not wear out. That's all. So there is a difference. Zinc is having low SRP. When zinc is coated, zinc undergoes corrosion. When tin is coated, tin has high SRP. It doesn't undergo reaction. That's why it is coated. But when zinc is depleted completely, then you have to coat it again. Here, when tin breaks, then iron undergoes corrosion rapidly. You should be careful. That's all. Okay. So this is one. Next, third one. There's something called cathodic protection. Cathodic protection. See, iron undergoes rusting because it acts as anode. If it is made as cathode, then it will not undergo oxidation. It will be protected. This cathodic protection, this particular method is used in case of protecting underground iron pipes. Okay. Iron pipes. Okay. So generally nowadays they use porcelain pipes and all. So previously when underground pipes were completely iron pipes carrying water or gutter water and all, what would happen? Iron undergoes a faster rate of corrosion in presence of dissolved electrolytes, especially in effluent water which is coming out of the industries or domestic waste. The iron pipes undergo rapid corrosion. Electrolytes catalyze the corrosion. That's why the vehicles which are in the coastal areas, their body will be more corroded than the vehicles in the non-coastal areas. For example, if we go to Mangalore and all, so it is the weather has a lot of sultry and humidity, and which contains salt in it. So the chassis and everything may be affected at a little more rate than the other places. Okay, so going for a second-hand vehicle from coastal areas should be at a risk. So you have to examine properly. That's why, especially in coastal areas, underground chassis will be coated with a polymer to prevent corrosion. That is also done. Fine. Coming back to this now. So underground pipes, iron pipes, may carry some electrolyte solutions in the form of the effluents or domestic waste and all. They will be corroded faster. In such cases, so if these are underground pipes, they connect magnesium strips here and there. Okay, so magnesium strips. So if you see in the electrochemical series, magnesium is much higher position compared to iron. Even magnesium is above zinc. So that means this iron pipes connected with magnesium strips. Being highly electropositive. Electropositive and possess very low SRP. What would happen? Magnesium undergoes oxidation preferably. So as it acts as anode, and iron thus become the cathode, will not undergo oxidation. So thus iron is made cathode by connecting magnesium, and thus it has been protected, cathodic protection. And magnesium strips can be periodically changed. So because pipe may be underground, not magnesium strips. Magnesium strips will be easily accessible and therefore can be replaced. So this is cathodic protection. This is also a sacrificial protection. Like zinc is sacrificed for the sake of iron, here magnesium is sacrificed. So these are things. Apart from that, there are chemical methods also. Like for example, very big iron containers, like it may be a container or a railway wagon which uses a lot of iron. How do? They take wagons and heat it to red hot and pass steam on the surface. So steam will convert the surface iron to Fe3O4. So Fe3O4 is quite stable and thus it can be protected. There is alloying. Chromium will be added to the iron to get stainless steel. Stainless steel is stainless, no corrosion. That's the meaning. No stain means no corrosion. Stainless steel contains chromium. Chromium actually, when present in the iron, it would be forming Cr2O3. Okay, stainless steel is an alloy of iron with specially chromium. How come this will be stainless or it is not undergoing corrosion? Here Cr would be present as Cr2O3, which is quite stable and which is there protecting iron in the surface. It will be forming Cr2O3 on the surface, and thus completely steel will be protected. So it will not undergo any chemical reaction. So this is the method for prevention of iron from rusting. Is that okay? So this is about rusting process. Next we'll take the last part we are at, that is batteries we need to study, and then products of electrolysis we need to study. So if those two concepts complete, the electrochemistry would be done. We'll take up now the concept of batteries. Okay. So in the remaining time, I think I can complete the complete concept of batteries. So I'll take up batteries itself. Then in the next class, products of electrolysis and the MCQs we can take. Okay. Shall we proceed now? Are you writing this? Is it complete?
Yes, sir.
Okay. I'll proceed. We'll take up the concept of batteries. See, when it comes to batteries, the battery technology has revolutionized the electronic industry, right? Now, with the lot of progress in the battery technology, you can see now the electric vehicles and two-wheelers have become common. They are even doing a lot of trials with heavy vehicles, heavy motor vehicles, whether batteries can be used to drive buses and lorry or trucks or something like that. Even for aviation, aeroplanes, can batteries be used like that? So a lot of innovation is happening in the field of battery. Of course, the most popular battery now, be it mobiles or anything, which is that? Is it lead storage battery? Which battery we are using now for everything? Lithium ion polymer battery. We say. Lithium ion polymer battery is the one which is proven to be quite efficient, has a higher recycle number of recycles and long life. So that means a battery is considered to be very good when it can be recharged for many times. So there should be higher recycle of recharging. So lithium ion is one which is also compact and relatively less weight and has long life. But it is expensive now. It has become of late very expensive. That could be one of the hurdles for a lithium polymer battery in the years to come, because it can't be used if it is very expensive. And of course, alternative batteries and combinations are being used. The people are telling that aluminum batteries and iron also is being tested. And in the due course, we don't know what is awaiting in store for us. If it is iron or aluminum, it would be definitely very cheap. They say that if the research is successful, the aluminum batteries which they use would be much more efficient than lithium ion. Okay. Meanwhile, if at all, if it is fine, this fuel cells based on hydrogen gas, if they become very convenient to use and popular, and all this lithium technology, everything will be replaced by hydrogen, because hydrogen fuel is the fuel of future. But that also has to be popularized and also should be made convenient to use. Fine. We'll come back to this batteries. What is basically a battery? We have studied the voltaic cell, right? Voltaic cell is a device in which the chemical energy converts to electrical energy. And battery is nothing but a voltaic cell. Sometimes a battery may have many voltaic cells connected in series or in parallel, or it may be a device which is similar to voltaic cell, which converts the chemical energy into electrical energy. So I can simply say the batteries are devices which are source of electrical energy. Which are source of electrical energy, where the chemical energy of a redox reaction, correct? Where chemical energy from where does this chemical energy comes from? Chemical energy of a spontaneous redox reaction is converted to electrical energy. Is converted to electrical. So this is a battery. So as I told you, it may be a combination of many voltaic cells. In series or parallel. Right. Okay. Now, so these batteries are of two types basically. Which are the two types of batteries? It is not that lithium ion battery or mercury battery or nickel cadmium battery like that. Basically, there are two types. Can you tell me what could be those two types? Because we know about it.
Rechargeable and non-rechargeable.
That's all. Okay. Rechargeable and non-rechargeable. When I say rechargeable battery, they are called secondary battery. Then non-rechargeable battery, what we call, is a primary battery. Okay. Two types. So number one, primary battery. What are primary batteries? In these primary batteries, these are non-rechargeable, chargeable, but as per the definition, we can say in this, the redox reaction, whichever is happening, which is responsible for generation of electric current, no, or voltage, that will be irreversible. It can happen only once. So we can say this is a battery in which cell reaction occurs only once. And that too, it is irreversible. Of course, since it occurs only once, we can say it is irreversible. Since it is irreversible, it occurs only once. Okay, and well, these batteries are kind of use and throw kind of batteries, because once the cell reaction is over, complete oxidation and reduction process is over, then it is useless. It can't be used it again. So the voltage drops and it has to be thrown out. And this is where exactly we have all the examples of different brands. Okay, Everyday, Toshiba, and which is that a toy boy which is running 10 times more than another toy boy running with the battery. Duracell, correct? No, so the Duracell, which gives the longer life, they say, no, they're all primary batteries. They can't be recharged. Of course, with respect to the utility and the life, it may differ, but they are all single time usage batteries. Okay, so what we need to study the examples under primary battery is something called dry cell or Lecland cell also is, and also mercury cell. These two examples. Next, the secondary battery. So the secondary batteries are those which are rechargeable ones. So in this secondary battery, what we can say, the cell reactions is reversible. Here the cell reactions can be reverted, it can be carried out for many times. So a battery which can be, we can say, battery in which cell reaction is reversible and can be used repeatedly by recharging are called secondary batteries. And these secondary batteries, in our syllabus we need to study something called lead storage battery. This we need to study in detail, but one more is there. Just there is a mention about this in its NCERT book, nickel cadmium battery. These, so they can be recharged and can be used several times. So apart from that, these two primary and secondary battery, which are based on chemical reactions here, there is something called fuel cell, which we study after this. Okay, fuel cell. What is fuel cell? That is hydrogen fuel cell. We'll see after these examples. Okay, so we'll take up now two examples under primary battery, dry cell, mercury cell, and two examples under secondary battery, lead storage and nickel cadmium battery. Okay, so we'll take up one. Yes. When it comes to the dry cell, first example, primary battery.
Sir, could you go back to the secondary battery definition?
Yes, I'll go.
Yes, sir. Thank you, sir.
Okay. So under primary battery, we are going to take example dry cell. This is also called Lecland cell. I think you would have used or seen in physics lab Lecland cell. Have you? You didn't use Lecland cell or dry cell in physics lab?
We didn't go to physics lab.
Yeah, physics lab.
We couldn't go, no, sir, this year.
No, last year. You didn't use in time for any circuits and all to power DC to the circuits.
No.
Oh, that's great. Okay. Now, any battery for that matter, what is common thing? There should be an anode and there should be a cathode and there should be electrolyte. And anodic oxidation, cathodic reduction, and overall cell reaction. This much we need to mention under each battery. Is that okay? So let us see which is anode and cathode under the dry cell. The battery looks like this. Okay. The writing diagram is not required for any battery, but since this especially Lecland cell is simple one, let me try out writing the diagram. This is actually as per they have given in the NCERT book. Okay, so we can also write a simple version of this, especially if it is this Lecland cell. Remaining batteries are all it requires three-dimensional representation, not required to write. Okay, so I would just go with this. Okay, so see the battery has anode and cathode. Which is anode? Which is cathode? Let's see. Anode is zinc here. Okay, zinc The container itself is anode. Zinc is anode, and the entire battery is made up of zinc container. Cathode is the carbon rod here. Of course, the carbon rod will be in contact with the powdered carbon and manganese dioxide, powdered MnO2. This entire thing is actually cathodic compartment, carbon rod in contact with powdered carbon and MnO2. Okay, the electrolyte. One second. It is the paste of ammonium chloride and zinc chloride. They don't use solution and all, otherwise it can't be made as a compact battery in using the solutions and all. It is paste or gel medium they generally use. Okay, so here in this particular case, it is paste of ammonium chloride, zinc chloride, which acts as electrolyte. Okay, now how does the cell look like? This is how, but we shall have our own methods of writing. As I told you, only for Leclan cell you can write the diagram. Remaining, only the details would be sufficient. Okay, so at the center there is graphite rod. Okay, this is at the center, which is the graphite rod, and this graphite rod extends outside. You would have seen there is a contact outside which is left there, and that will have a brass tip on the surface. For electrical contacts, this is a typical battery which we see, right? So this is graphite rod with a brass tip. It is used as a cap. Okay, and for better sealing, there is one seal that they use with a polymer or anything like that. One second. So this is the seal. Right. Now I told you this graphite rod is in contact with the carbon powder and MnO2 that we need to mention here. Okay. So this graphite rod is in contact with carbon powder and MnO2. So I'll just show it in the form of these dots. You can simultaneously, right? Okay, to give this a shade, let me go for this. Okay. complete black carbon rod. Yes. So this zinc container, as I told you, the container itself is the anode, which is made of zinc. Okay, this is zinc container. The anode. Carbon rod, cathode. Powdered carbon plus MnO2. And what is there here? In contact or in between this cathodic compartment and the anode, there is electrolyte, paste of ammonium chloride and zinc chloride. So you can show with the slightly different dots and color. So this is paste of ammonium chloride and zinc chloride. Which is electrolyte. Fine. So this is our Lecland cell or dry cell. This is how you can write in the exam, no problem. Now we'll see cell reactions. So anode and cathode. What is the easy guess? Anodic oxidation, no? So zinc undergoes oxidation, losing its electron. Two electrons. Correct? Whereas at cathode, so manganese dioxide is there, no? MnO2 cathodic compartment. Along with that ammonium ion from the electrolyte and an electron will be reduced to a compound which is MnOOH, manganese oxide hydroxide, liberating energy. Then we may get the doubt that if ammonia is liberated out during the reaction, the entire dry cell should stink like ammonia, pungent smell. But none of the batteries, even the dry cell, has any smell, correct? So ammonia, if it is liberated out, then nobody would use it, despite of whatever the significance. The batteries, if it is brought to the home, then the entire room will be stinking with the pungent smell of ammonia. So what actually the thing happened? This zinc ion, which is formed due to oxidation, would combine with ammonia to form a complex here. Zn2 plus combines with NH3 and forms a complex ion like this. Zn NH3 4 times 2 plus. And this complex will be there inside the battery. Okay. So this is the overall cell reactions that are responsible for generation of electric current. And typical dry cell would generate the cell potential. Okay. The cell potential of 1.5 volt. Okay. Of course, one problem is when the battery is new, the potential will be at max 1.5 volt. As you keep using, with the usage, the potential reduces. It becomes 1.3, 1.2, 1, something like that. And at the end, you have seen if these batteries are used in a torch, when the life is almost near the end, you would not get the brightness at all. So that means the voltage would have dropped. So in the life cycle, as per the usage, the potential drops down. That is one of the disadvantages actually. In the beginning, it gives very good voltage. At the end, it doesn't give. So when the brightness completely goes down, we'll throw it out. So this is about the Lecland cell or dry cell. Need to know cathode, anode, electrolyte, cell reactions importantly. Come on, write down this. Let me know once if it is complete. See, it is quite common thing that children will play with these batteries and try to break that open and see what is there inside and all. You also would have done in your childhood, and you would have seen some kind of paste and all coming out, which will have a kind of stink. Huh? Uh, so those are all the electrolytes mixture, anode, cathode. Sometimes anode and cathode is also a different material which is used in the form of gel itself. You can also write overall reaction, multiply the second equation by 2 because 2 electrons are there here. 1 electron is required in the next reaction. Multiply by 2 and then add. That's all. If it is complete, I'll proceed to next part. Done. Fine. Hope you have written down. I'll proceed to next. The second primary cell example we are going to study is mercury cell or battery, you can say, no problem. As the name itself suggests, there is mercury, so therefore it is called mercury cell. You would see this diagram. Okay, in the exam, if you want, you can write. It's otherwise not required. Okay, so have you seen this kind of cells anywhere used? Did you use any time this kind of cells?
Watch.
Watch. That's all. Hmm? So it may be any small equipments. Generally, it may be watch or even toys. Okay, wall clocks again, or any other systems where little electronic equipments are there. Generally, these kind of button cells are used, right? So one advantage of this mercury cell is the potential doesn't fade away like the way dry cell. In the beginning, it will be 1.5, and at the end, it may reduce to very low, right? So whereas these mercury cells, they give constant voltage. That is one of the advantage for that we have to use these mercury cells in the watches. If you use dry cell kind of batteries, in the beginning it shows correct time. As the life goes towards the end, the time will be delayed. As such, now you are coming 5-10 minutes delayed to the classes. If it is dry cell used in the watch, then after the class only you will join. So mercury cells, one advantage is they give constant voltage in their complete lifetime. Okay, voltage doesn't drop down. So what is cathode, anode, and all? Let's see now. It's a very compact battery. Here, the anode is what is this called? ZnHg. What can be it called as?
Zinc amalgam.
Zinc amalgam. So zinc amalgam is anode. Then what about cathode? Cathode is paste of mercury and the carbon. The paste of mercury and carbon. And also electrolyte is also a paste. Paste of KOH and zinc oxide. Okay, anode, cathode, and electrolyte. Now, what are the cell reactions? At anode. Here, especially zinc takes hydroxyl ions from the electrolyte, becomes ZnO, plus what else can be obtained? Water, and 2 electrons will be liberated out. Oxidation. At cathode, this mercury oxide along with water takes 2 electrons and become mercury, liberating those 2 hydroxide. This is actually mercury oxide. Paste of mercury oxide and carbon is cathode. Okay, so mercury oxide of cathodic compartment will take electron along with water to form mercury and OH. If you want, you can get the overall reaction by adding these 2 reactions. Cell reaction. What are the things will cancel? 2 OH and 2 electron. Okay, so then the overall cell reaction responsible for EMF is zinc, HGO, this water also cancels, giving rise to ZnO plus Hg. You can see zinc undergoes oxidation, anode, mercury oxide undergoes reduction, cathode. That's it. And the voltage cell potential developed here is around 1.35 volt, and it is constant for the entire usage of the battery. Okay, so it is used in watches, toys, hearing aids, remote control, so all these things. Of course, little expensive compared to the dry cells. Come on, write down this. Is this complete now? ಏನಪ್ಪಾ, should I go forward or stop or stand for lifetime here? ಏನ್ ಮಾತಾಡ್ಬೇಕು ಸ್ವಲ್ಪ?
Finish.
ಏನಾಗಿದೆ ರೀ ಜನಕ್ಕೆ? We'll take secondary battery. The example is lead storage battery. Here, anode, cathode. As I told you, this is secondary battery because it can be recharged. Say the cell reactions can be reversed. Electrolyte. Here, anode is lead. Cathode is also lead. But only difference between anode and cathode is anode is lead rods and cathode is lead grid, we say. Grid means a combination of many rods or plates together is what is called a grid. So lead grid, it also has some quantity of lead dioxide, PbO2. That's the only difference. That's the cathode. So lead is anode and lead grid with PbO2 is what is cathode. Excuse me. So electrolyte is 38% aqueous H2SO. So acid batteries also we call because these batteries contain acid in it. Okay. So these are the anode, cathode, and electrolyte. So what are the reactions? Let's see. At anode. When I write these reactions, these are secondary battery, right? They can be discharged, that means to get the electric current, and they can be recharged to store the current. Now, when I write the reactions, it is during discharge. Even previous cases are also, when we write the reaction, it is for discharge of current. That means conversion of chemical energy into electrical energy. So, what actually happens at anode and cathode? Let's see. At anode, Pb combines with sulfate ions to form PbSO4 and electrons are released. At cathode, PbO2 present in cathode again takes sulfate with H plus ions of the medium and electrons to form PbSO4. And what is this? Remaining 2 oxygen, 4 hydrogen, it becomes 2H2. Like this. So, if you want overall reaction, add it. The overall cell reaction, 2 electron get cancelled. See whether anything else to cancel. Actually nothing. Okay. So here Pb plus PbO2 plus 2 sulfate and 4 H plus. Can I write it as 2H2SO4? No problem. 4H plus and 2 sulfate, right? So 2H2SO4 giving rise to 2 lead sulfate plus 2H2. So this is the overall cell reaction during discharge. So cell reaction during discharge means when it acts like a voltaic cell or galvanic cell. Chemical energy to electrical energy. Is it okay? Since it is a secondary battery, we should write what are the cell reactions during the recharging or charging simply. What could be, shall I simply reverse this like PbSO4 plus 2 electron to the left hand side, Pb plus SO4 to the right hand side and write? Would it be fine? I'll just reverse it and write. Will it hold good? Can anybody tell me? During charging. Charging means what? You are going to pass electric current and bring about chemical reaction. A device in which electrical energy converts to chemical energy is called what? Is called what, sir?
Electrolyte.
Electrolytic cell. The device where chemical energy converts to electrical energy, voltaic cell. During charging or recharging, what actually happens? Electrical energy converts to chemical energy. That is the characteristic of an electrolytic cell. Okay, if you want for your clarity, you can write electrical energy to chemical energy. Chemical energy. That is what it happens. Okay. So will it be sufficient if I just reverse these reactions and write, like for example, during recharging, both the reaction gets reversed. So I would write Pb SO4 plus 2 electron, products reactant, reactant product, Pb plus SO4 2 minus, and I'll write second reaction reversed, PbSO4 plus 2H2O giving rise to PbO2 plus SO4 2 minus plus 4H plus 2 electron. So is it sufficient enough? Shall I write first reaction anode, second reaction cathode?
First reaction cathode.
That is one thing it is important to note. Just not reversing at respective electrodes. You cannot write the same reverse reaction in the anode, because anode is always oxidation, cathode is always reduction. So when you reverse the first equation that was taking place at anode, then products become reactants. Then electron will be added. Addition of electron is reduction. So reduction takes place at cathode. You have to reverse equation and change the anode and cathode also. So this becomes cathode now at cathode. As reduction is happening, this becomes anode as oxidation is happening. Correct? Then the overall cell reaction, only electrons get cancelled. This will be exactly reversed. 2 PbSO4, 2H2O, PbO2, 4H plus 2 sulfate is 2H2SO4. So they would ask you, especially for this lead storage battery, cell reactions at anode and cathode during charging, during discharging, when it acts as a voltaic cell, or when it acts as an electrolytic cell, or when electrical energy converts to chemical energy and vice versa. So there can be confusion, should be very clear. Should be very clear with respect to at least any one direction. During discharge, you should be very clear. And reverse it and change the anode and cathode. Then it becomes the reactions at electrodes during recharging. Come on. Write down and let me know.
Sir, after we use excessively,
Hmm.
if the battery gets swollen, no, sir, what will happen?
Here they use a kind of spongy lead in this grid. That spongy lead is nothing but the powdered lead which has been compressed to the grid here. Okay, the powdered lead will be compressed and will be used in the form of grid. So after many recharge cycles, this spongy lead will be not as compact as that was there in the beginning, and all the contents will not be compact enough, and thus the recharging reaction wouldn't efficiently happen like the way it happens in the beginning. So there will be a kind of swelling that happens, especially in some batteries, not everywhere, especially in these secondary batteries. And that happens, you would often see in case of lithium polymer battery, right?
Yes, yes, sir.
Mm. Shall I scroll down now?
Yes, sir.
Excuse me, sir.
Yeah, tell me.
Sir, won't the water affect the conductivity?
See, water, especially, it is formed and only it will decompose during the recharging, otherwise not. So overall amount of water would remain same unless you are going to add, or dilute anything like that. So it doesn't make any difference.
Okay, sir.
Okay. Shall we proceed now? We have one another battery just to mention. And this is the lead storage battery which is extensively used in vehicles and all, right? So you have this 12-volt battery, 6-volt battery and all. These are all generally these lead storage batteries only in trucks and all you see. Okay, shall I proceed now?
Yes, sir.
Nickel cadmium battery. Okay. Here only cell reaction has been given, just to remember, but I'll give you a little more details. The anode, here is cadmium. The cathode, actually it's a compound of nickel. Nickel 3 oxide hydroxide. nickel 3 oxide hydroxide, NiOOH like. This is nickel oxide hydroxide. And the electrolyte is the alkali base, that is KOH. Okay. The overall cell reaction here, as per your NCERT book, cadmium interact with this NiOH thrice to form cadmium oxide plus NiOH twice plus water. You can see here 0, 2 plus. So this is undergoing oxidation. Oxidation, therefore anode. And nickel is 3 plus here, is changed to 2 plus. So plus 3 to plus 2 is gain of electron, reduction, and it is cathode. And this is the diagram. Actually, they use this anode and cathode in the form of layers, and in between there will be a separator. A separator generally will be a polymer, which will be used in any battery. Anode and cathode will be generally separated by a polymer. In especially nickel cadmium, polyamides will be used. Whereas in case of this mercury battery, you have seen this, there is a separator again. Okay, this is polyethylene, polythene otherwise, separate. Okay, so these separators are important. They separate anode and cathode compartments. Otherwise, the mix up and potential generated would not become will become zero. Fine. Okay, it will not be generated. So a separator will be used, and anode and cathode will be used in the form of layers, and it will be rolled inside. And this nickel cadmium battery is also found to be very efficient battery, and gives a relatively a better voltage for long time and better recharge cycles. That means life of the battery is better. So of all this, the lithium polymer battery is what people prefer now. But only one hiccup could be its costliness. Okay, so it becomes very expensive in the days to come also. Okay, so this is about primary and secondary batteries. We have one another battery, that is fuel cell, we need to study, and also products of electrolysis. Probably the next class theory gets completed. Okay, so if you have any doubt, you can ask me. Otherwise, we shall end up the class now. Yes, if it is complete, you can leave. Thank you.
Thank you, sir.
Thank you. Yes, I'm going to end the meeting.